Good evening, everyone. This is Amish Panchal from Castwell Foundries. We welcome you all to the second episode of Nodutalk, organized by Castwell. As we all have enjoyed the first episode, and we have learned a lot from Dr. P.K. Basutkar about the chemical composition of ductile iron and how to get a carbide-free structure in a S-cast condition. After encouraging response from the first episode, today we have come up with a second episode. Castwell, since its inception, has worked towards the spreading the technical knowledge for the betterment of the SGRN industry in India. In past, we have conducted several. In past, we have conducted several 3 days workshop, 3 to 4 days workshop, as well as 1 day seminars related to SGRN production practices and best practices, you can say. Nodutalk is just another thing in our pursuit to spread the knowledge. Next slide. Next. Next. As most of you know, Castwell produces ferrosilicon magnesium inoculants, high quality carburizers, and we also deal in a high purity pig iron called sorrel metal, which is in some of the SGRN castings it is necessary. We participated in IFEX 2025 at Calcutta. It was a very good response. Our stall was bubbling with many of the visitors. Next. During the IFEX 2025 at Calcutta, we released a Nodutips Tamil version, and it has received a warm response from the many of the foundry men, particularly from the southern India. Those who are not familiar with what Nodutips is, it's a 1 point lesson. We have compiled about in a first booklet. We have compiled about 100 such tips, which is available in English and Hindi language, and to reach to the more and more foundrymen, and particularly to the shop floor people, we have come up with this Tamil version of the Nodutypes. Those who want to get their free copy, kindly write to us. We will courier it to you. Next. Yeah, so coming to the topic, today in episode 2, we are going to cover effect of minor elements in SGRN, carbide free and good structure in S-cast condition. Next. Our expert speaker will be Dr. P.K. Basutkar, who is having 55 plus years of mastery in metal castings. Many of you are knowing him. Still, he has worked throughout his career. He has worked in a General Motors USA, and thereafter in a Tata Motors foundry at Pune. And throughout his career, he has assisted many small, medium, and large size foundries to upgrade their production practices, problem solving, and defect solving in the foundries, and particularly in SGRN castings. So, next. Uh, this will be the content of the today's topic: heredity. What is the heredity in iron melts, particularly in SGRN? Carbide promoting elements in ductile iron, subversive elements, then summary of the effect of residual elements in a ductile iron, and foundry solution to the carbide issues. Friends, last time also we have observed that many of you were not asking or discussing your problems. The basic idea of this talk series is not to give you the knowledge, because now the knowledge is available across internet, and many of the books are also there. The idea is more and more interaction and finding the solutions to your problems. This is our earnest request that yeah, if you come up with the problems beforehand, then we can analyze with our expert team and we can try to give you some of the solution. Yes, we know that the foundry is a very vast subject, and not one person can give you the exact solution. But at Castwell, with our expert team, we will try our best to give you the good solution. Now I hand over to Dr. Basudkar for his talk.
Thank you, Amish Bhai. Thank you very much. Namaskar. Good afternoon to all of you. Uh, Last time we spoke about the five basic elements in ductile iron: carbon, silicon, manganese, sulfur, and phosphorus. We saw that to produce ductile iron, you have to have we have a very small window in which to make good quality ductile iron. On the left hand side, we have limitation that the carbon and 1/7 of the silicon should be more than 3.9%. That was seen last time. We also saw that in order to avoid the graphite flotation in any SGN castings, depending upon the section size, we have got limitation on the carbon equivalent, which can not exceed the given value for various section thicknesses. We saw this thing last time. Upper and lower limits being the silicon content. That depends upon impact, shrinkage, tendency, so on and so forth. We didn't speak too much about the sulfur last time, and we'll speak about sulfur and oxygen in order to make the carbide free and good structure in as cast condition. Yeah, we'll speak a little bit about hereditary metal in iron melts. There are a lot of properties of SG iron which cannot be explained only by the composition or the metallurgical practices which are used in making SG iron. We used to call them earlier as something to do with the hereditary properties of the raw materials and the processes used, mostly raw materials. So we'll speak a little bit about the hereditary properties of iron melts. Okay? Then we'll speak about the carbide promoting elements, subversive elements, and so on and so forth. Next slide, please. Traditional belief was properties beyond which can be explained by composition and metallurgical practices were inherited from the charge. Currently, it is understood that heredity from the charged materials is very, very, very complex. It depends on liquid metal condition and solidification behavior of the charged materials. Different charged materials supply different level of oxygen content to the base metal. Please underline this thing. Different charged materials supply different level of oxygen content to the base metal. This is one of the most important reason why we have to keep the charged materials constant and of same quality throughout our AGIN campaign. Different charged materials supply different levels of oxygen content to the base metal. Then excess of oxygen in liquid metal is prevented in the case of SGN because of the high carbon present in the present in the liquid metal. Carbon doesn't allow oxygen to build up, so the high level is prevented. But low level depends upon the magnesium treatment. Oxygen plays a role in the nucleation and the growth of the graphite nodules. Too low oxygen level is undesirable. It promotes carbide. Example, in metal treated with pure magnesium, like a Fischer converter process. The oxygen level and both sulfur level cannot be too low in HGN from the point of controlling the structure. If sulfur is too low, we end up with non-spiral graphite shape. If sulfur is too high, we end up with flake graphite or vermicular graphite. If oxygen is too low, we end up with inverse chill. So there are limits to which we can reduce the oxygen. Sulfur is not much of a problem, but oxygen control is a problem in HGIN. So this is why we always say for making good quality HGIN, keep your raw materials and process control very, very, very closely controlled. Changing raw materials or process variations causes problems in HGIN quality. Last time we could not discuss one important issue, which was the quality index, which we will discuss in one of our subsequent episodes. So quality index takes into account how to prepare and how to make sure that the quality of the HGR is first class. We'll speak about the quality index subsequently after we understand what are the things which spoil the quality of HGR. Next slide, please. Superheating the metal leads to carbide formation. High temperature leads to destruction of graphite nodules in the melt. There are two aspects to this thing. Higher temperature, more carbides. You see in the figure below, the figure A is metal at the maximum temperature of 1360 degrees centigrade. no carbides, beautiful nodules, high nodularity, lovely nodule count. This is one of the most important requirement of HGIN. If you superheat the metal, like the slide under B, it is superheated to 1760 degrees. You see all those structures between the graphite nodules, they are carbides. They are very, 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 very strong carbides. Sometimes these carbides cannot be annealed out by high temperature heat treatment process also. So never superheat the metal, and never hold the superheated metal at high temperature for a long time. Both time and temperature of superheating control the detect and do the carbide stabilization. So you must avoid unnecessarily superheating the metal and unnecessarily holding the superheated metal at a high temperature. Carbide in ductile iron are undesirable because they reduce ductility, they reduce the soundness, they cause shrinkage in the casting, they reduce the impact resistance of the casting, and they affect the machinability. Last time I was speaking about the composition, I had mentioned to you that in all HGIN, the manganese level should be as low as 0.3% and not to exceed 0.3%. Because in liquid metal, if the manganese is 0.3%, in heavy section HDI and castings, in the center of the section, the manganese segregation takes place up to 10%, 10 times that value. If it is zero point 0.3 in the liquid metal, 10 multiplied by zero point 0.3 is equal to 3%. So there will be 3% manganese in the center of the section, which forms so stable carbides, those that carbides cannot be even drilled. If you put a drill over there, the drill will get blunt and eventually the drill will break, but the carbides will not give way. The different types of carbides which you can encounter in HGIN. The types of carbide is first the eutectic carbide, which is a chill caused by low carbon equivalent. The second one is the inverse chill. Normally, we expect chill carbides to be formed on the outer surface in contact with the mold. But inverse chill is the chill carbides formed inside the section of the casting. That's why it's called inverse chill against the outer chill, which we normally refer to as chills. Then there are carbides which are segregated in the cell boundaries. Cell boundaries are the boundaries between two nodules, three nodules. The carbide which segregate in the cell boundaries. These are the other types of carbides, and we will be speaking about the elements which form the carbides. The carbide stabilizing elements are manganese. I just spoke to you about it. Chromium, vanadium, boron, and tellurium. Let's discuss these elements one by one. Chromium is a very, very strong carbide former. Its limit is 0.05. Last time when I showed you the figures for different wall thicknesses, the carbon, silicon, manganese, copper, along with the limits for sulfur, phosphorus, chromium, and nickel, I indicated that the carbide of manganese will form if the manganese content is more than chromium content is more than 0.05%. Chromium carbides persist even after long annealing at high temperatures. Above 0.1% chromium, carbide removal via annealing is difficult. Chromium is used in abrasion-resistant applications of SGIN, where it is used up to 0.3%. In austenitic ductile ions, carbide enhances oxidation and corrosion resistance. So it has its own application, but in our charged materials, we have to make sure the carbide is chromium is less than 0.05%. That's why you have to segregate your gray iron returns in which we use chromium and HG returns. Make sure that the gray iron returns don't get mixed up with the HG returns and form the form of raw materials for HGI. Vanadium is another carbide former. It's a very, 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 very strong carbide former. The safe limit for vanadium is 0.03% to avoid ash cast carbides. At 0.2 to 0.3%, you will see in the graph, vanadium increases the tensile strength and the proof strength on the top and the hardness, and with minor impact on elongation and toughness. So vanadium is to be avoided. It is used in some steels to improve the weldability. But vanadium is a poison as far as SGN is concerned because the carbides are very, very strong carbides. Boron is a carbide former. It's an extremely powerful carbide former. As little as 0.002% boron can cause intercellular carbides. It severely reduces the mechanical properties. The elongation drops from about 14% to 1% at 0.01% boron. Can you imagine? Elongation of HGIN dropping from 14% to as low as 1% at 0.01% boron. Boron carbides are highly stable and cannot be removed by annealing. Boron neutralizes the pearlite forming effect of copper. If boron is present in your pearlitic iron, it will not give you the hardness. It reduces the hardness of pearlitic cast irons, SGIN. Limit of boron in pearlitic iron is 6 ppm, 0.0006%. 6 ppm is the limit for boron in pearlitic ions. It does not have that much bad effect on ferritic ions, but it is extremely bad if it is present in pearlitic ions. The source of boron is steel scrap, ramming mass, and silicon carbide that people use. And it's a good material to be used, but make sure the boron is less than 6 ppm in pearlitic ions. Tellurium. Tellurium as a carbide former, it is used to control pinholes, and the maximum amount of tellurium required to control the pinholes is 0.003%. At more than 0.01%, tellurium promotes strong carbides. We'll see the tellurium carbides in one of the photographs later on. Tellurium is used in thermal analysis cups to induce carbonic mutative solidification to get the correct carbon equivalent values. But most people, after use, they throw these cups into the melt. Never, never, never put this tellurium coated cup samples into the melt. Make a hole in your foundry at the back and dump them and bury them. Don't use thermal analysis cups with tellurium we put into the melt. Never put these tellurium cups in the melt. Avoid recycling of tellurium-coated thermal analysis cups into ductile iron charged materials. Look at the graphite degenerated by tellurium with magnesium 0.05 and tellurium is less than 0.01%, and you see the graphite. When the tellurium gets to 0.015%, the entire graphite structure becomes gray iron, flake graphite. You see this? Only the small difference is the flakes are not so sharp as in gray iron, they're rounded off, but it is completely gray iron structure when the tellurium is exceeding 0.015%.
Friends, we have covered the carbide forming elements so far. Regarding boron, I would like to share one of the experience of our customer. They were getting it was a fully ferritic structure, but the elongation was not coming. We initially we failed to find out what would be the root cause because it was a fully ferritic structure and still the elongation was not coming. Then someone told that let us change the scrap and see. So we changed a scrap and conducted the trial, then everything was okay. So boron mostly comes from the steel scrap, and their concentration is such a low that with our normal spectro calibration, it is we are unable to identify and judge its values. So it is a very risky and with high alloying scrap which is coming, particularly automobile, because all the automobile manufacturers are going for thinner and thinner gauges with a higher tensile strength and a higher strength to lightweight the vehicle weight and to increase the efficiency. So they are alloying with chromium, manganese, aluminum, boron, and vanadium particularly. So these are all subversive elements for our ductile iron production.
Subversive elements are the elements which spoil the nodular shape of the nodules of graphite in SGIN. They destroy the nodular shape of the graphite. That's why they are known as subversive elements. Some elements, when present in very small amount, interfere with the spherical graphite formation. These are called subversive elements. Magnesium. Magnesium is very essential for making HGN for spheroidization. Magnesium, both at the low level as well as the high level, causes subversive graphite. If magnesium is very low, it causes either flake formation or compacted graphite formation, which is also known as vermicular graphite. If magnesium is very high, more than 0.07%, it causes spiky graphite formation, which is not acceptable. If magnesium is higher than 0.1%, it even forms magnesium carbide. So it eventually gets graphitized and you get spiky graphite in HDIN structure. So both magnesium, although it's an essential element for making HDIN, both low magnesium as well as high magnesium are subversive as far as the graphite shape is concerned. Cerium is required to be present for two reasons. One reason is it is a neutralizer. It neutralizes the bad effect of all the subversive elements. So cerium is required because we can't check each and every piece of scrap that we are using. We do not know what subversive elements are present. So not knowing what subversive elements are present, we always use cerium as a mixed metal or rare earth in the magnesium treatment alloy. Cerium is required to increase the nodal count. It also causes chunky graphite formation if it's in the high level. My slide which I showed you in the last episode, it indicates the maximum level of cerium in HGIN for all the wall thicknesses, less than 12 millimeters to more than 650 millimeters, 0.025. Cerium is required to neutralize the bad effects of the subversive elements. It's also required for good nodularity and good nodal count. If cerium is present in excess, it promotes chunky graphite, especially in heavy section. And this graphite is just not acceptable to the customer. The whole casting will get rejected if chunky graphite is present. Carbon and silicon, high levels in slow cooling lead to graphite flotation and exploded graphite, which we saw last time in our slides, which give you the very small window for making HDIN. Covered with, on the left-hand side, carbon plus 1,7 silicon more than 3.9%, carbon plus one-third silicon more than size. It should be controlled to avoid graphite flotation. So high levels of carbon and silicon cause graphite flotation. This is a list of subversive elements which are known to promote chunky graphite on the left-hand side: cerium, calcium, silicon, nickel, and carbon. The elements which are known to promote intercellular graphite. That means the graphite in between the nodules. Flake graphite, mostly this flake graphite or different shapes of flake graphite. So elements which are known to promote intercellular graphite are bismuth, copper, aluminum, lead, antimony, tin, arsenic, cadmium. These normally come from non-ferrous scrap pieces that may enter into the charge mix used for melting HDN base metal. Then the elements which are known to promote deleterious graphite, graphite which is affecting the mechanical properties and ductility and all the good properties of HDN are known as deleterious graphite. And the elements which promote this bad quality graphite are zirconium, zinc. Nowadays, all the cars are using zinc-coated steel strap at the zinc-coated steel for their undercarriage cover to prevent corrosion. And the zinc-coated scrap is very, very bad. As far as possible, do not use any zinc-coated scrap in your foundry. First of all, during melting, the zinc vaporizes from the liquid metal and falls like snowflakes, and the foundry platform becomes white in color like snowflakes. The other one is selenium, then titanium, nitrogen, sulfur, and oxygen. These are deleterious elements. Now, just remember, if there are so many elements which can play havoc with our HDIN, how can we know which element is present? First of all, our spectrometers are not having channels to detect these elements. And in some cases where they have the channels, we don't have the standards to calibrate the channels to know at what level these elements are present. Because if we know at what levels these elements are present, we can use cerium to neutralize the effects by adding cerium at least to the same level to which these bad elements are present in the liquid metal. So the literature elements are so bad and their detection is so difficult and their levels are so difficult to analyze because the standards are not available to calibrate the channels on the spectrometer. So Make sure that you use rare earth containing ferrosilicon magnesium for the magnesium treatment. If you are making very, very, very large castings, then I'll give you a tip. Most people avoid the deleterious effects of these elements in very, very, very large castings by taking 50% ferrosilicon magnesium with cerium and 50% ferrosilicon magnesium required without cerium. So both of them put together will give you casting without deleterious elements and without chunky graphite. Because heavy sections, if the cerium is more than 0.025, you get chunky graphite. So making heavy sections, keep this tip in mind. Use 50% ferrosilicon magnesium with rare earths and 50% ferrosilicon magnesium without rare earths for cerium to react with these bad elements as well as cerium to avoid formation of chunky graphite if it is present in excess of 0.025. Nitrogen forms flake graphite. Nitrogen comes from nitrogenous nitrogen containing binders, resins used for making the cores. Nitrogen is one of the elements which is very difficult to detect. The only way you will know nitrogen is present is by looking at the microstructure and the flake graphites, where the casting is cast against the green sand mold, where there is no nitrogen present, you again have got beautiful ductile ion structures. So nitrogen from resin binders promotes flake graphite at the surface of the casting, and these nitrogen layers may not get removed even by 3 millimeter machining. So you have to be careful that you coat your resin coated binders with nitrogen with some kind of a coating which will prevent the effect of nitrogen in forming flake graphite. Effects of aluminum. Aluminum comes from aluminum kiln steel. It also comes from high silicon steel. So please do not use high silicon steel in your steel scrap just because you want to increase the silicon. The aluminum plays havoc with the SGIN microstructure. It comes from aluminum kiln steel. It comes in ferroalloys. It is required to some extent ferroalloys, and it is present in inoculants to make the inoculants very effective. And the limit is 0.5% aluminum is more harmful in thick sections. Pinholes are promoted by hydrogen pinholes are promoted by aluminum. And vermicular graphite is formed. Flake former can be controlled by adding cerium. So when aluminum is present, you have to make sure that you're using cerium to take care of aluminum. In the first place, please do not use aluminum containing steel scraps, especially high silicon steel scrap, which is having high levels of aluminum. Effects of antimony and arsenic. Above 0.004%, they causes mesh type of graphite in heavy section. Mesh type of graphite, look at the structure A. Antimony was added deliberately 0.005%. Look at the beautiful structure of graphite. But when there's no antimony, you have got mesh type of graphite. Our 0.004%, it causes mesh type of graphite in heavy section. Pearlite promoter affects ferritic structure. Antimony is useful in countering chunky graphite in heavy sections. So when you use antimony to avoid chunky graphite in heavy section, you have to also use a little bit of cerium to compensate the bad effect of mesh graphite formation of antimony. So if you are going to use antimony to control chunky graphite in heavy section, make sure there is some cerium present as much as antimony is required to be added. Antimony and arsenic have a very peculiar effect on the graphite formation segregation. Graphite appears partly as very round nodules, extremely high nodularity, and when the antimonies are not present, that graphite will look like radius type of flake graphite all connected. In chunky graphite, the graphite particles are all isolated. In this type of segregation with antimony, the graphite particles are all connected. They form a graphite flakes all connected, not like chunky graphite. Effects of antimony and arsenic. You look in the microstructure with arsenic and antimony degenerated the graphite. The graphite particles are nodular in most cases, but in between the nodules. These are the cell boundaries. In between the nodules, you see the graphite has been generated and formed mesh graphite, spiky graphite, flake graphite, and this is what will cause deterioration of all the mechanical properties of HGIN. Antimony and arsenic are both elements which do not react with magnesium. The effect of antimony and arsenic begins when antimony is present up to 0.004%, and when arsenic is present as 0.01%. But the good point is that the effect of these bad effects of antimony and arsenic can be neutralized by the addition of cerium, which is the rare earths present in the ferrosilicon magnesium alloy. So you have to have ferrosilicon magnesium alloy with some rare earths to make sure that the subversive effects of all the elements which you do not know which are present in your charge mix get neutralized, because cerium does this as very effectively. Effects of bismuth at 0.003%. Bismuth promotes intercellular flake graphite. Look at the microstructure. In between, the graphite nodule is also deteriorated. It's not fully nodular. And in between this graphite nodules, you have got cellular graphite, intercellular graphite, which is like flakes. The flakes are not sharp, but this is a very dangerous structure to have. Your mechanical properties will be even lower than the gray iron properties. The effect of degeneration for bismuth and lead starts when the content is more than 0.002% to 0.004% and will be increased with the presence of copper. If copper is present more than 0.5%, the effects becomes worse. If these elements are present along with copper and tin normally is never 0.5%. Tin is about maximum 0.05%, 0.06%. But when copper and tin are present together, these elements can play havoc with the graphite structure in HDI. Fortunately, their effects can be neutralized. Bismuth effect can be neutralized with the addition of cerium. So you have to use rare earth containing ferrosilicon magnesium treatment alloy. The result will be a reticular or a mesh-like network of graphite. It also increases the carbide formation due to other elements present along with the bismuth, used in thin section castings to increase the nodule count. Bismuth is very effective in increasing the nodule count and decrease the nodule size very strongly in thin sections. But when you're adding bismuth, you have to make sure that you have cerium to neutralize the bad effects of bismuth. Bismuth forms compounds with magnesium. So the amount of residual magnesium which is required for making HDiron, if it is on the lower side, some magnesium will be taken away by this bismuth as it forms compounds, and the magnesium content will be below what is required to form good quality HDiron, which is 0.035%. So bismuth forms compound with magnesium, and therefore you have to keep the magnesium around 0.045, 0.048% to avoid the loss of magnesium due to formation of compounds with bismuth. Effect of lead. The lead is a very dangerous element to be present in any raw material. Lead causes flake graphite. Look at the microstructure. The full structure is full of flake graphite. You hardly see any nodules over there. As little as 0.002% lead causes flake graphite, especially in heavy section castings. It contaminates iron via scrap steel, counterweights, and leaded steel. There are some steels with lead content deliberately added alloying elements, but if that steel comes into your raw materials, you will have a havoc with your HDI casting. Minor contamination of lead is countered or neutralized by the effect of ferrosilicon magnesium containing cerium. So, since you do not know exactly how much of this subversive elements are present, I recommend very strongly that you use rare earth containing ferrosilicon magnesium alloy to neutralize the effects of all these bad elements which are present to some extent or the other in your charge materials. Hence, control of charge materials, especially raw materials, as well as process controls, is extremely important. And we'll speak about this thing in details when we speak about the quality index, which is one of the basic requirements of the quality index being high in HDN casting, is to have a control of raw materials and control of process. Effects of titanium. The titanium is one of the most dangerous elements that can be present in raw materials. It is naturally present in pig iron, especially Indian pig irons, because along with the iron ore, there's titanium ore present in the raw iron ore, which are used for making pig iron and steel scrap. Maximum level of titanium is 0.035 accepted. But look at its effect on the graphite structure. Figure 4.16, flake graphite caused by high titanium. As the titanium content increases, look at the figure on the right. As the titanium content increases, the magnesium required for making HDI also increases, because titanium eats away the magnesium. But the worst part of this titanium is the effect on this carbide formation. Titanium promotes flake graphite as we have just seen. It increases the poisoning effect of the previous elements present like lead, bismuth, tellurium, antimony, and arsenic. It forms carbides, and the carbides cannot be seen at lower magnification. And the only element that can neutralize this bad effect of titanium is cerium. Once again, good enough reason to use rare earth containing ferrosilicon magnesium. In rare earths, cerium is present up to 40%. So that is good enough to take care of all these bad subversive elements which we are unable to detect, unable to determine, and unable to take any action. So having cerium acts like a good neutralizer for all the subversive elements. Look at the effect of titanium degeneration at graphite in the figure on the left hand side. Hardly any graphite nodules. And the graphite nodules are all disturbed. They can hardly be called nodules. When titanium is present at a very high magnification, you can see it forms cubic titanium carbides. These titanium carbides can be seen on the right hand side figure. And these are very hard carbides, cannot be removed by heat treatment. Titanium is a very dangerous element, especially when it is present with other subversive elements. It causes havoc in your SGI pass. Effects of cerium. We have seen that cerium forms stable compounds with titanium. 0.01% cerium and 0.07% titanium helps retain spherical graphite. Cerium causes irregular and chunk graphite without complementary trace elements. If the trace elements are absent, then cerium causes chunky graphite. So cerium is both a friend and an enemy. If bad elements are absent, then cerium should not be used, otherwise it will form chunky graphite. If bad elements are present and cerium is not used, then we have got these elements of graphite formed in the microstructure. So both you have to be careful and you should be knowledgeable enough to find out if bad elements are present and use cerium, and if bad elements are absent, do not use cerium. The only way is we can't remove these elements from the metal. We can only dilute these elements to some extent by using high quality pig iron like Sorel pig iron. Bad elements, their effects can be neutralized by cerium, but if the bad elements are present, to a large extent, cerium will help. But if the bad elements are absent, the cerium will promote chunky graphite. So you have to be very careful and be very vigilant when your raw materials enter the foundry. Particularly, cerium is problematic in austenitic SGIN and it's removed upon remelting. Cerium has got a very high melting point, around 2500 degrees centigrade. So it does not vaporize when you prepare liquid metal. It gets into the slag and is removed a little bit to the slag. Otherwise, the cerium is very difficult to remove from the material. In remelting, it never gets vaporized. It remains to some extent, but on a very small extent. Most of it goes in the slag and gets oxidized. This is a summary. I think it will be useful for you to tell your scrap supplier to make sure that where are the sources of these bad elements coming from. Aluminum, antimony, arsenic, bismuth, boron, cadmium, chromium, lead, tellurium, tin, titanium, vanadium, zirconium, their levels which are required in as pearlite promoters in ferritic ions, as carbide promoters in pearlitic iron, and degeneration graphite promoters at what levels. And the sources are given over here. Please make sure that your steel supplier has this information so that he doesn't get the wrong elements in your charge materials. What are some of the foundry solutions to carbide issues? Consistency in raw materials and control of trace element levels is critical. Understanding element interactions helps minimize defects. Innovation in alloying practices continues to enhance the HDI quality. Optimize nucleation for better graphite structure. Avoid excess superheating. Proper magnesium treatment and use of lethal inoculants to optimize nucleation of spherical graphite. Cerium and other rare earths additions help neutralize the bad effects of subversive elements, and using high purity charged materials such as Sorel metal, minimizes unfounded trace element buildup and effect of silicon. Please remember, we have got lot of problems with these subversive elements. We cannot afford to have channels in our spectrometer for having this to detecting the subversive elements, and we cannot get the standards to calibrate the channel to know exactly how much amount of these subversive elements are present in our charge mix or a liquid metal. Therefore, please make sure that you use rare earth containing ferrosilicon magnesium, and make sure your cerium is not very high in heavy section castings. We have given you the control limits for cerium, chromium, sulfur, phosphorus in the last time in the slide, along with the carbon, silicon, copper, and
Dr. Saab, I'll start. One of the question is that bismuth is considered as a subversive element or a bad
yeah,
element for ductile iron. But
yeah,
nowadays in market, there is a inoculant with bismuth is available. So
yeah,
how this contradiction is happening?
yeah. Well, this is not a paradox. This is right. As I said, bismuth promotes very small nodules, and it gives you a very high nodule count. Especially bismuth is recommended for thin sections for getting very high nodule count. And very high nodularity nodules. And because of this, when you add bismuth, and bismuth being a subversive element, if it is not compensated by or neutralized by its bad effects is neutralized by cerium, then bismuth will give you problems of non-spheral graphite. Small amount of cerium is required in thin section casting to increase the nodule count and to increase the nodularity. The nodularity is almost 100% when bismuth is used in thin wall castings. But to neutralize the bad effect of bismuth, a little amount of cerium is to be added, almost equal to the amount of bismuth which is required in the inoculant.
And one more phenomena, Dr. Saab, we have observed that for heavy castings, people have started adding antimony to some extent. So what is the logic behind that?
Yeah, antimony is, see, in heavy section castings, the nodule counts are very low, sometimes as low as 25 or even lower than that thing, depending upon the thickness of the casting. So to increase the nodule count in heavy section casting, antimony is a good inoculant when present to a small extent, but because of its bad effect, subversive effect on the graphite structure, the antimony when it is used in heavy section casting to increase the nodule count and the nodularity, it should be compensated to avoid this bad effect by adding a little bit of cerium, but make sure that the cerium and bismuth, there's a relationship which we gave over here. What is the effect of cerium? Is a question by Devi Prasad Vyas. What is the effect of sulfur? Now, I forgot to mention in the first episode the role of sulfur. Thank you, Mr. Vyas, for reminding me. In the base metal, before magnesium treatment, our sulfur level should be 0.00014 to 0.16. Of course, if the sulfur is more than that thing, you have to desulfurize the metal before the magnesium treatment. If the sulfur level is after magnesium treatment, should be between 0.008 to 0.012. If the sulfur level is below this level, then you have got non-spiral graphite. The graphite not reduces. There is a minimum to sulfur required to be present in SGIN to make sure the sulfur does not form manganese carbides in SGIN casting. What should be the level of calcium in heavy section? Calcium should be less than 0.035, and if the oxygen is too low, it forms inverse chill in the castings. So oxygen levels about required is about 25 ppm, 25 to 35 ppm. But it's very difficult to analyze oxygen. So you have to just make sure that it is not too low. There's
Yeah.
one question we appeared here: how much nodule count should be 200 millimeter section? Nodule count around 150 in 200 millimeter section.
Yeah. Then Mr. Vishal Prajapati is asking what is the difference between magnesium with rare earth and magnesium with lanthanum? Please, if you could explain in brief.
Well, lanthanum is a very effective magnesium treatment alloy. It's good, but when lanthanum is present, cerium should be absent. In the rare earths, we have got cerium, we have got lanthanum, we have got neomium, and we have praseodymium. So when lanthanum is present in magnesium treatment alloy, it's a good element to be present. It, but cerium is required for affecting the effects of subversive elements. When subversive elements are not present, it is a good element to be present in magnesium treatment alloy.
Good evening, sir. This is Joshi calling from Foundry, Belgaum. Actually, my casting section thickness is more than 10 mm. It is about 10 to 15 mm, and the grade is 600 by 3.
So in 600 by 3, 10 to 15 millimeter section, you have to get the it's a ferritic grade.
No, it is a perlatic grade. Actually,
Then you have
90%.
to add, and in the ferritic grade you are getting ferrite, is it?
Yes, sir. Yes. Yes.
I suggest very strongly that you take a look at your boron level in your liquid metal. I think boron is playing havoc with your quality grade of casting. Boron is a culprit. I very strongly, my intuition tells me that boron is playing havoc with you in your quality grade casting. It also causes. Is the hardness okay?
Hardness is also okay, sir.
Is okay.
All mechanical properties are okay, actually.
Uh-huh.
But only in microstructure, if I check the micro, no, so
Yes.
it is 90 to 95% perlite, but some carbides are there that associate with perlite, and it is around like 3% ferrite, but it is also associated with carbide.
Okay. Now, first of all, in microstructure thin wall casting, there may be some carbide formation because of the inoculation may not be okay. Number one, you can try some late inoculation. Number two, the polytic structure having a very small amount of carbide. Is there any, if the boron is not there, then look at some other elements in your raw materials, carbide forming elements. And the third thing which I want to tell you is when you describe your microstructure in your reports, see, there is about 10% is the graphite nodules, okay, because of the carbon present. 10% of the microstructure before etching, if you see, the graphite which is present is occupied about 10% of the microstructure. So 10% is graphite, and the remaining 90% is carbide, ferrite, stellite, pearlite, and other elements. If you're having some carbides, is it carbide or is it stellite, phosphorus? What is the phosphorus level?
Phosphorus is point not 25 to point not 35 max.
Okay, your phosphorus is okay. It's less than 0.035. So phosphorus should not be forming steadite in your cell boundary areas. So it is not a phosphite problem. It is not boron problem. And your hardness is okay. So it's not a boron problem. And you're still forming some carbides. So I think you should take a look at your inoculation practice.
My inoculation is 0.4% streamline. That is 1 to 3% size. And
Sorry, please repeat that. 0.3% steam inoculation.
0.4%.
0.4% steam inoculation while pouring the mold.
When we transfer the metal into ladle.
Okay. When you transfer the treated metal into the pouring ladle, you're adding about 0.4%.
And 0.02% post inoculation, cerium inoculation.
Okay, 0.02% steam inoculation. Well,
Yeah.
0.02% is a little bit on the higher side. 0.15,
Point not 27%.
not to 7%. And that's a little bit low, isn't it? We go up to 0.15% steam inoculation, that is while pouring the mold.
0.15.
That is maximum. Then the size should be around 0.2 to 0.6 millimeters.
Yeah. Point two point. Present I am using 0.2 to 0.7%.
Okay, that is fine. That's fine. Yeah.
Okay.
If you are using a filter, you can put the steam inoculation below the filter in the mold, so that the
Yeah.
metal will get inoculated from the beginning of pouring to the end of pouring. And then after the knockout, you should see some undissolved ferrosilicon particles in the bottom of the sprue.
Okay,
Okay,
sir.
thank you.
We have two questions. One
Yeah.
is by Mr. Vishal Atkari. How to select percentage carbon and silicon based on the wall thickness of the casting, which helps to get eutectic solidification. So I have replied, we have covered this in episode 1 and we will send him the table. depending on the section thickness, what should be the carbon and silicon content.
See,
Then,
no, I want to add a little bit to him.
yeah,
To avoid the utility carbide, the foundry must find out how much is their carbon loss during the magnesium treatment. Normally, don't depend on the carbon and silicon analysis on the spectrometer after the magnesium treatment. If your carbon loss is more, you are likely to have low carbon equivalent, and that can give you carbides in the microstructure. So please try to find out if you can how much is the average carbon loss in your foundry. How much is what is the quantity of metal you're doing the magnesium treatment? Quantity of metal. If the metal quantity is around 1 ton or so, you are likely to lose about 0.15 to 0.25% carbon during the magnesium treatment. If the metal quantity is lower than that thing, you might lose even more carbon during the magnesium treatment. As the quantity increases, the carbon loss decreases because of the violence of the reaction.
then sir, one question from Mr. Bhagwan Bharat from GN Tech is there. Hello, sir. If we take a tapping temperature of 1480 degrees centigrade, then is it okay metal or is it a superheated?
No, 1480 is okay metal. But important thing is your pouring temperature should be sufficiently high for thin section and sufficiently low for heavy section. Sufficiently high means 1420, 1440 for thin wall castings up to 3, 4, 5 millimeter wall thickness and 1360, 1380 into thicker section casting. So if you want to get the required pouring temperature, you should not go beyond 1500 degrees tapping temperature from the furnace. 1480 is very good temperature. Okay, you have to keep this temperature 1480 and reduce the temperature loss by putting some kind of insulation inside your pouring ladle after magnesium treatment, so that the temperature loss is minimized and you still get your required pouring temperature when you're pouring the molds. 1420 to 1440 for thin wall castings, 1380 के आसपास for thick wall castings without increasing the temperature in the furnace. 1480 is a very good temperature for tapping the furnace for magnesium treatment.
There is one more question from Mr. Vishal Prajapati. Why do we need a minimum sulfur level of 0.008 to 0.012, as you told, and also told by my seniors, but I don't understand the concept. From whatever little I know, sulfur should be as low as possible. Please, could you explain?
Well, if you can't afford to make sulfur zero, then you will not have any graphite at all. Sulfur is required to make sure that you don't form uh, manganese carbides in SGN casting. Most of us in foundries in India use a higher level of manganese, and therefore to prevent the formation of manganese carbides in thick wall castings, you must keep sulfur level as low as 0.008 minimum, and up to 0.012%. If the sulfur is lower than this thing, then the graphite nodularity gets disturbed. The graphite will be less than 85% nodularity. This is especially seen in magnesium treatment processes using pure magnesium methods, where sulfur level goes down and you have to keep higher sulfur around 0.05 or 0.06 before magnesium treatment to get around 0.016, 0.014 sulfur in the metal after magnesium treatment. Sulfur is required to prevent carbide formation.
Then one question is by Mr. Satha Sivam. Sir, what is the minimum treatment metal weight is good for ferrosilicon magnesium?
Well, in the in-mold process, you can have minimum about 8 kilos of metal for magnesium treatment when you have an in-mold process. And I have made such castings in Pune in one of the foundries for short blasting machine wear plates. So minimum metal is not a criteria. There are methods of doing magnesium ferrosilicon treatment even with 5 or 6 kilos of metal by the in-mold process. So uh, it can be anywhere from 100 kilos, 150 kilos to maybe 25 tons, 35 tons, 45 tons.
Okay. Sir, I would like to add what we have seen from our 50 years of experience. Lowest treatment of what I have seen at one of our customer is about 15 kg. Just like a small
Fa-
handshake,
fa-
he was doing a treatment and pouring because the section thickness and castings were very small. Of course, you have to select the size of the ferrosilicon magnesium accordingly.
Right,
Then
right,
you
right.
can do. And
Yeah.
there was no pocket. It was like a open treatment. And of course, lowest we have seen so far is 15 kg. And as you rightly said, for inmold, 8 kg also can be possible.
The Fiat Foundry was making in-mold treatment process for making AGIs from as low as uh, 12 kilo castings up to maybe 170, 180 kilo castings. But that foundry has closed down.